Okay, good morning, everyone. Hope you have enjoyed a great fall break. But just to remind, our deadline of our homework 2 is due on this Friday. So you haven't started, please start right now because it do need some time to debug a code and then run your program to get the results. Yeah, first I want to emphasize that our TMs and TA mentioned some students forgot to provide some running script like run.sh. Please do provide that. Otherwise, we cannot execute your code. Right? We do need to run your code on the kid machines and say if the results match what you report in the homework assignment. And also, they haven't tried their best to run that, but if you don't provide some running script, if we cannot replicate your results, then your grading will be affected. So I think the TM has made an announcement in Canvas. So just want to emphasize again. And the second thing is about I think I have repeated for many times, but again, I will request everyone to start doing homework early and seek for help early. So I heard some complaint that there's kind of a congestion in office hours. I can understand because there are like several days to the deadline. But since the starting from the release of the homework 2 until the very last week, like the office hour is always empty. And so don't try to like ask questions, seek for help in the last 2 days or even 1 day. Although we try our best to, we allocate like 5 hours office hour, on Friday, which is the deadline. But if like 20 or 30 students are asking for help, that might still be insufficient. So again, we appreciate that if you can start working on them or looking at them early. At least you know which problems you feel challenging or you need help. So you can first look at those problems and ask for help. Otherwise, it will be really difficult to get help in the last minute. Okay, and we're gonna release our homework 3, I think tomorrow on this Friday. But don't worry, homework 3 is the workload is much lighter because it's mainly about perceptron. So we have a wrap up the perceptron. Everyone agrees that it's kind of straightforward algorithm and the variants are straightforward, but we do request you guys to start early as well, right? So I kind of like skeptical that you can, like if you start doing that at last day, it might still be quite inefficient and you might still get panic that. Okay, so any question regarding the homework assignments and other things?
I was just wondering on homework 2, do we have to deal with the weightage examples for the
Yeah.
I was wondering if an acceptable way of doing that would be to take care of the weighted sampling of the data set and train on that piece, or should we just do the fractional count?
If you're implementing the AdaBoost, you should use the fraction count technique, right? I don't know how to do. If you do weighted sampling, maybe it works for random forest, those kind of stuff. But for AdaBoost, please do use the fractional counts. Otherwise, you won't get the results as you expected. Yeah. Other question? Okay, so if you still need help for homework 2, or in both the paper problems and program sections, please feel free to stop by the office hour today. I'm in my office, and I'm willing to help you. And also, please leverage the office hours tomorrow. We still like a lot of hours tomorrow. If you do need help, just stop by. Okay. Okay. So today we're going to talk about things a little bit more related to theory, but don't worry, it won't be in depth. and you are not required to prove any theory. We just want you to understand those theory results, because we're going to use them to motivate the next algorithms called support vector machine. Right? So support vector machine is viewed as like most successful and insightful and beautiful machine learning algorithm in the past 2 decades. I can later share some gossip about support vector machines. So we're going to talk about another topic in computational learning theory today, which is called agnostic learning. And then based on agnostic learning, we want to introduce the concept called VC dimension. So later we'll explain what is VC dimension and why the VC dimension is invented. So briefly, what is agnostic learning? Right? So basically, it gives us an analysis framework about the generalization error when you cannot guarantee a zero training error. Okay? And in this case, can we still estimate a bound for the generalization error or true error? Right? And about VC dimension, this will be related to our previous analysis. Right? When we talk about sample complexity bound, we say, okay, we use log size of hypothesis space to indicate the complexity about your model, right? However, what if your hypothesis space is infinite? If you take logarithm of the size of an infinite hypothesis space, it will still be infinity, right? And then all sample complexity bounds are useless. So VC dimension was invented to address that problem. Like even you have an infinite hypothesis space, you can still get a finite measure over its expressiveness or complexity. So let us kind of like review what we have discussed previously, right? So previously we do some kind of analysis for a particular type of learning scenario, which we call consistent learning. So basically we assume, okay, your learning algorithm is so powerful and your hypothesis space is so rich such that whatever training data set you give to your learning algorithm, it always finds a hypothesis with zero training error. Right? This is our previous assumption. Right? So under this assumption, meaning that, okay, every time, no matter what kind of training data set you got, right, I can always find a hypothesis with 100% accurate training accuracy, meaning that it can perfectly fit every training example. Then we can derive a sample complexity bound. Right? This is something we have shown that before. I use some like a probability union bounds, right? So it says that just like let's just read through this to refresh our mind. So if given some probability delta or confidence level delta and some error level epsilon, if the number of training examples is bigger than this guy, that is 1 over epsilon times logarithm of size hypothesis space H plus logarithm 1 over delta, the confidence in level. If M is bigger than this guy, then we claim that with probability at least 1 minus delta, so roughly can rule this with high probability, and then your learned hypothesis, which has zero training error, will have true error, namely the generalization error less than epsilon. So basically it gives us an insight that, okay, how many examples you need at least to ensure that your learned zero training error hypothesis will perform well in the generalization, right, with high probability. And here we emphasize that we must stay with high probability because we cannot guarantee you always, or you have 100% sure to get a very good hypothesis in terms of the generalization error, right? Because the trained data is random. Right? You cannot guarantee that you will never encounter a bad quality trained data set. Right? So this is our results and analysis based upon a very ideal assumption that, okay, the learning algorithm is powerful, your hypothesis space is really abundant and rich, such that every time you got the training data, whatever training data you get the zero training error of your learned hypothesis. Right. So let me emphasize the assumption again. First, the training and test examples come from the same underlying data distribution, which is reasonable, applies to all kinds of computational learning theory development. And then for any concept here means target function, right? There is some function in the hypothesis space that is consistent with the training set. So that is our assumption about the consistent learner. Right? For any target function, and based on the labels of that target function and the data set generated from some data distribution, and then you can find a hypothesis in your hypothesis space which can correctly label all the examples. Right? So what does this assumption imply? Right? This is a very, very strong assumption, right? For the labels generated by any target function, the concept, right? For any training data set, your hypothesis, your learning algorithm can always find a hypothesis in the hypothesis space that exactly match the labels provided by this target function. What does it imply? Any thought? In what kind of cases and what kind of choice of hypothesis space can give you such a strong guarantee? Okay. So actually, it implies that your target function is actually inside the hypothesis space chosen by your learning algorithm, right? And for any target function in your concept space, here's inside this red circle. Right? Because we assume consistent learner, right? That means, okay, for arbitrary data set labeled by your target function, you can always find a hypothesis in a hypothesis space, which gives exactly the same label. Okay? So the only reason can give you such a strong result is that, okay, the whole concept space is contained in your hypothesis space, right? If any target function is outside, right? So there must be some data set which can capture the difference between the labels by this outside concept and all the hypothesis hypotheses in a hypothesis space, right? So it's not possible that for any data set, your hypothesis space can give you a hypothesis which exactly match the labels by the given by the target function, right? So that's a very, very strong assumption. So any question in understanding this point? Mm-hmm.
Why would it not be
Yeah, that's a good question. So actually, even your concept space, this red circle C, is inside your hypothesis space, right? It does not guarantee that, okay, for this particular hypothesis space, given a particular data set, your learning algorithm will always identify the exact concept. I might just find some hypothesis nearby. There's a capability of the search problem.
What if there is a function that has the same sort of values as two functions for all these same data, but the
Yeah, yeah. Yes. Yeah. Yeah, that's exactly the point I made. It doesn't, it cannot guarantee that because your training data set is always finite, right? So that means for any finite data points, right, one function match that, another function can match that as well, right? So that means you might have like many choices of different functions or hypothesis space to give the consistent prediction, but they do not necessarily overlap.
Such function, then why would say that there exists a hypothesis hedge in that space. Is it consistent with varying samples? Imply that the quantum space is within the hypothesis, contained within the hypothesis. If there could be some function which is kind of like,
yeah, that's the point I've just emphasized. Like remember, our assumption is that any data set, you can always find a hypothesis. It's not just for one data set. If it's for one data set, well, it's not necessary, right? You might have many different hypotheses which give exactly the same prediction. However, we're talking about any data set. You can always find a hypothesis which gives exactly the label as the target function. So you can imagine, okay, if your let me draw something, right? If your concept is here, right? So of course, for some data set, you might find some hypothesis here might give exactly the same prediction. Yeah, this is possible. But can you guarantee, like for any data set labeled by this guy, you can always find a hypothesis which it gives exactly the same label? You cannot. Right? So that everywhere or arbitrary assumption actually implies this strong conclusion. Does it make sense? Any other question? But let me emphasize key point again, right? So if there are some concept outside of this hypothesis space, right? So you know that there must be difference between this concept and all the hypotheses in the hypothesis space. Right? So that means there must exist some kind of data set which can reflect such difference, right? Where the labels made by this concept will be different by labels made by any hypothesis in this hypothesis space. Right? Otherwise, if for any data set, the prediction made by this concept is exactly the same by some hypothesis space, then there won't be any difference between your concept and some kind of function inside this hypothesis space, right? We cannot capture that. Does it make sense? Okay. So now, a natural question is, why should we presume that your concept class be inside the hypothesis space? This is a very strong assumption. It's actually it's actually not realistic. Right? So imagine that, okay, if you want to learn some linear classifier or you want to learn neural network, right? You actually don't know what is target function. So can you tell me what type of function which reflects mapping between today's stock price and tomorrow's the stock price at tomorrow? You don't know that, right? And no one tells you because we really don't know. So it is possible that, okay, your concept class actually is not inside a hypothesis space. Right? This is more realistic. So what if a concept F, which we are trying to learn, use hypothesis space in H, but F does not belong to H? In other words, the whole concept class, namely the family of the target functions, is not a subset of your hypothesis space. So they might overlap, but the whole concept class does not necessarily belong to this big H. So this setting is called agnostic learning. Okay. So why it is agnostic? Because I really don't know what does the concept class look like. Okay. If you want to make a prediction, you want to predict temperature of tomorrow. Right? You don't know what is the concept class, what is the target function. Right? It might be some sine function, it might be cosine function, it might be it might be some high order functions which are even not analytical. You don't know that, right? And no one tells you that, right? When a meteorologist and physicist, they just write down a set of partial differential equations, right? And in many cases, partial differential equations, the solution won't give you an analytical form. Right? You don't know what exactly the target function look like. But when you use machine learning to learn that, well, we always assume, okay, this is a linear function, or this is a kernel regression problem, which is actually some kind of form we're going to discuss later. This is a neural network, right? These are all parametric form. Right? These are parametric form, but does not necessarily exactly contain all possible target function. Right? So that means agnostic learning is more realistic. Right? It's actually the most practically useful assumption we should use. Right? Then the question is, under the agnostic learning setting, can we say something about sample complexity? Suppose if you still want to reach some certain level of the generalization error, of course, with high probability, how many examples at least we need to use? Okay. So to answer this question, we need to first be aware some properties of agnostic learning. So the most important property we should be aware is that the training error will not guarantee to be zero. Right. Why? Why on the agnostic learning we cannot assume your training error is always zero? Yes, exactly, right? It's actually another kind of explanation of agnostic learning setting, right? If your target function is outside your hypothesis space, that means there must be some data set where the labels given by your target function cannot be exactly recovered by any hypothesis in hypothesis space. Right? If you break the assumption, that means your target function must be inside hypothesis space. So we cannot guarantee zero training error because there may be no consistent hypothesis in the hypothesis space because the target function can be outside the hypothesis space. So then what is our goal, right? Our goal is still tries to have low training error as small training error as possible. Okay? So we still want to find a hypothesis in a hypothesis space that has training error as small as possible. So basically, you can imagine this is like amount we're going to search over this hypothesis space, right? And if you want to achieve a training error as small as possible, we expect that we can find some hypothesis which is as close to the target function as possible, right? And of course, we cannot guarantee we got zero training error. We cannot guarantee the closest hypothesis is exactly the true concept, right? Because the concept can be outside your hypothesis space. Right? So again, if you look at the definition of the training error, and here we still consider the binary classification problem. So the training error is the fraction of the training examples that are misclassified. Right? So basically, you look at how many examples are misclassified by a hypothesis, meaning that their labels do not match the labels given by the target function, right? Divided by the total number of the training examples, you get a training error. So any question regarding the setting of the agnostic learning? Right. So first we'll break the basic assumption, the ideal assumption that we got zero training error always, right? It is possible we don't have a zero training error. Right? We still try to fit the data as much as possible. That means we want to get a low training error, right? But it is not necessary to be zero. Right? And we expect that by find out a hypothesis which has small training error, this hypothesis could be close to the true function or target function. Okay, this is our setting. So what do we want? Right? We want that, okay, given this small training error, it might be 0.05, 0.03, or 0.1. We still want this hypothesis will have a good accuracy on future same examples. Namely, we still want our generalization error to be small. Right? So the task, one of the key tasks in agnostic learning is that, okay, can we derive an estimate of the generalization error in terms of our small training error in hand? That's the major task in analyzing agnostic learning. So a natural question will be, how can we do that, right? We got some small training error, right? How can we derive some bound or some kind of estimate of the generalization error, right? So doing this, we'll leverage some probabilistic tools, which are called tail bounds, right? So later we'll see how we can smartly leverage those bounds to derive the generalization error based upon the training error. Okay? So what are tail bounds? In general, you can will like those bounds quantify or estimate the chance that the random variables get far away from its mean. So we know that in probability or statistics, we know that random variables like Gaussian random variable, Laplace random variable, many random variables. The most likely places they appear will be surrounding the mean, right? And the far away, the farther away the random variable jumps from its mean, the smaller the chance. Right? So tail bounds just give you some tool to estimate how much chance your random variable will jump far away from its mean. Any question? Okay. So what are commonly used tail bounds, right? So here we briefly introduce two inequalities. One is called Markov's inequality. The second one is called Chebyshev inequality. I guess you have seen them in your statistic textbook before, right? So what is Markov inequality? So it bounds the probability that a non-negative random variable, right? So here we have some restriction. The random variable must be non-negative. Exceeds a fixed value. So basically says, if a non-negative random variable x, we have such an x, right? Then the probability that x take a value more than a, this probability is upper bounded by the expectation of x over a. Right? So you can imagine that the larger the a you have, the smaller the upper bound, right? So the expectation of x is some kind of constant, right? So you can imagine if you choose a to be very, very large, like 1 million, then you divide your expectation by 1 million. So this bound is very small. Right? So it basically reflects the meaning that, okay, the farther away your random variable jumps away from the mean here, the lower the chance. Right? So Another commonly used inequality is called Chebyshev inequality, which bounds the probability that a random variable, so this random variable can be positive, can be negative, right, differs from its expected value by more than a fixed number of standard deviation. So basically it requires you have the second order information. You got mean, you got the variance. So given such a random variable x, right, we know its mean mu and its standard deviation sigma, right? So it tells us that the difference between x and mu, when this difference is bigger than k standard deviations, this probability is less than or equal to 1 over k squared. Right? So basically, okay, this is your mean, right? This is your mean, and random variable can take whatever values in the range, right? But the chance that it's going to take some value, okay, might be here or might be here. This value from mu, the difference is bigger than k standard deviations. This chance will be no bigger than 1 over k squared. So you can imagine the larger the k you have, the smaller this probability. Right? It also reflects the same meaning that the farther away your random variable takes the value from the mean, the smaller of that chance to happen. Any question? That's related to how you derive the Markov inequality. The derivation of Markov inequality is really, really simple. You just look at any like standard textbook, it will tell you. But yeah, as you mentioned, you actually point out some like some kind of weakness of the Markov inequality because it doesn't consider the standard deviation information. That's why they get a relative like weak upper bound. But also reflects the idea, right? Our intuition. And then Chebyshev inequality is a bit stronger in that it incorporates the standard deviation information, and also it does not require your x, the random variable, to be non-negative. These are just the two cases to explain our intuition, right? But here we're in our agnostic learning setting, we're not using these two inequalities. We're going to use the third one, right? This one will help us to bound the average of random variables. Why do we want to bound tails of average of random variables? Because the training error depends on the number of errors on the training set. Right? So if you go back and take a look at the definition of training error, right? So essentially, how do you compute the training error? We just look at every training example and say an indicator. Right? An indicator is 1, meaning that, okay, you make a wrong prediction. 0, meaning you make a correct prediction, right? And you just add them together and do the average. That's your training error. So essentially, the training error is an average of a set of independent, identically distributed random variables. That's why we're going to use the so-called Hopkins inequality. So what is Hopkins inequality? And but again, there are like two-side version of Hopkins inequality and one-side version of Hopkins inequality in our setting. Using one-side version of Hopkins inequality is enough. So Hopkins inequality can upper bound on how much the average of a set random variable differs from its expected value. Right? So here, I mean, we're talking about the general case. Suppose we have m identically distributed, independent identically distributed random variables, ID random variables, x1 to xm. So we denote by p bar as the average of those m ID random variables. Be careful, this guy is still a random variable. Don't get confused. This guy, you do an average of set random variables, it's still a random variable. However, if we take expectation of that random variable, each random variable, which denoted by P, it is constant. Right? So because all x1, x2 to xm are ID, that means it take expectation of any random variable, they will be the same. Okay? So let's denote it by P. And then the Hopf inequality tells that the true mean expectation or true mean of those random variables is epsilon away from the empirical mean. Empirical mean means the average or mean of those random variables. This probability is upper bounded by an exponential factor. So e to the power of -2 m and epsilon squared. So m is number of random variables you average. And epsilon is just the distance epsilon inside the inequality. Okay. So let me emphasize again, right? This is very important for us to understand the meaning of Hopf inequality, although you are not required to prove that, right? So P here indicates the true mean, right? So like there's one coin, right? You know some kind of underlying true probability that you have heads up, right? So this is constant. And if you toss a coin, and this is random event, right? And the head is up is 1, or heads down is 0, right? So the mean of this random variable will be the true mean, will be the probability you see the heads up. Right? That's binary random variable. And then P bar is the empirical mean, right? So we don't know actually the true mean or the underlying the probability of this coin that you see the heads up. How can we do that? We toss the coin many times, right? We assume those each tossing is kind of independent. Then we just look at heads, tails. We just count how many heads are up, right? And look at the fraction. This is called empirical mean, right? And then Hopf inequality tells that, okay, the true mean, the probability that the true mean is epsilon away from the empirical mean is upper bounded by this exponential factor. Any question? Yeah, I mean, I'm just use the one example. But in general, you can view like, sorry, P is just the expectation of those ID random variables. But here we just use one example, like we use a coin as an example, right? So if you toss a coin, you want to look at whether it has head up, right? So this random variable is a binary random variable, right? And the mean of the random variable is the probability you see the heads up, which we call true mean, right? But of course, in practice, how can we estimate the true mean? We just toss the coin like many times, 100 times, and look at, okay, out of this 100 times, like maybe 61 or heads up, then I estimate the mean, the true mean to be 0.61. But this is just the empirical mean. This does not necessarily give you exact estimate of the true mean, right? And this Hopf inequality just tells you how do you bound this estimate error, right? So it tells us, okay, the true mean is epsilon away from the empirical mean, which you get from tossing many coins, tossing the coin many times, is upper bounded by this guy. Yeah. That's the next point we're going to discuss right now. But I do want to make sure everyone feels comfortable with this inequality. I understand the meaning of that. Any question? Okay, so now let us look at this inequality. You can see that this is kind of a very strong result. So first, this is the exponential factor. So we know that when m increases, it decays very fast, right? It's exponential decay. And even stronger, if you increase epsilon, it decays like exponentially and quadratically. It's very strong, right? So that basically means that, okay, if you average a large number of the IID random variables, then your true mean will be very close to your empirical mean, right? And or the chance that it is quite far away from your empirical estimate is very, very low, right? Because it's less than some exponential to the 2 minus 2m epsilon squared, right? And similarly, the distance epsilon is more, the result about distance epsilon is even stronger, right? So if you increase epsilon, you can see that this upper bound decays even faster. So both m and epsilon, which determine response, shows us that, okay, your true mean or true expectation of random variable won't be very far away from your empirical estimate of the mean or empirical or average of the random variable. Does it make sense? Yeah, m is the total number of the random variables you average, right? Suppose you have m random variables. Epsilon is something you designate. Like you want to say, okay, how far away, like epsilon takes to be like 0.1, right? So you want to say, okay, what's the chance that the true mean is 0.1 away from the empirical estimate? What's the chance of that? And this inquiry tells that, okay, it won't exceed e to the power of minus 2m and 0.1 squared. So what this tells us, right? Takeaway is that, okay, the empirical mean will not be too far away from the true mean if there are many, many samples. Because you increase m, you know that it decreases exponentially. Right? You increase epsilon, it decreases exponentially quadratically. Right? So now let us get back to the agnostic learning setting. Right? We can consider the true error, also known as the generalization error, to be the true mean. Why? Right? This is the definition of the generalization error, right? Which we have seen it many, many times. So the definition of the true error is that, okay, if you randomly sample example from your instance space following some data distribution, underlying data distribution, or D, and what is the probability that the prediction made by your learned hypothesis is different by the label given by the ground truth. Right? So if you define this as a binary variable, right? This is actually binary indicator variable, right? So this is essentially the probability that a binary random variable takes value 1, right? And just to define as an indicator whether my prediction made by H is different from the prediction made by the target function F, right? And because the input to this function, like xi, are some random variable sampled from the underlying data distribution D. So this indicator itself is a binary random variable, right? And the true error, essentially, the probability this binary variable is 1. Okay. So the probability of a binary random variable is 1 is actually the mean of this binary random variable, right? This is statistical knowledge, right? You got the binary random variable, right? Let me just use I, right? So we know that I is 1, the probability is P. At 0, the probability is 1 minus P, right? So you tell me what is expectation of this random variable? What's that? It's just P, right? It's just P, right? You just apply the formula, right? It's a p, the probability 1 times you take the value 1 and plus the probability 1 minus p times, forgive my bad drawing, times the value 0, right? So the mean of this binary random variable is actually the probability that this random variable takes a value 1, right? So that gives us the result that, okay, the true error essentially can be viewed as some mean of this binary indicator random variable. It's a true mean. Now let us look at how we compute the training error. Look at this again. Right? The training error essentially is computed by, okay, going over all M training example, right? And for each training example, you just look at the corresponding binary indicator. Right? If there's 1, meaning that you make a wrong prediction. If there's 0, you make a correct prediction, right? And then you just do an average of those n binary random variable. You see that? Right here, right? And each training example xi are sampled from the same underlying data distribution D as well. So that means those binary indicators, like for every training example, are ID, and they follow the same distribution of the binary indicator we use for test. Right? So in other words, our training error essentially is the empirical estimate of the true error, right? Because your average of those indicators actually is an empirical estimate of the true mean. Does it make sense? Right? So it's like you can view like this is like toss a coin, right? So our true error essentially the probability you make wrong prediction, you can make analogy like just like you see a heads up, right? So that's the true error, or we can view this true mean. And now for the training error, you can view like, okay, I have M in training example. That means, okay, I toss the coin for M times. Okay? And just to look at for each tossing result, whether you see the heads up. If it's heads up, it's corresponding to a prediction mistake, right? And now you just average those indicators, right? Like you say, okay, out of like M tossing coins, you have like 10 heads up. That means you have 10 mistakes, and then you do the average, they do 10 over M. That's your training error. Right? So this essentially gives you an empirical estimate of the true error. Does everyone see that? Everyone sees that point? Okay. And now we can apply the half density equality. Okay. Oh, right. We want to ask. So first, we see that the true error or the generalization error to be the true mean. And the training error over M examples essentially is an empirical estimate of the true error. And remember, the training error is still a random variable. Why? Because every training example itself is a random variable, right? You do the average of those indicators over those M examples will still be a random variable. And we want to ask, what is the probability that the true error is more than epsilon away from the empirical error? Like suppose your training error is 0.05. Right? I want to ask, what is the chance that your generalization error is actually 0.04, like 0.01 away from the training error? What's that chance? Of course, we want that chance to be as small as possible, right? But we need to first bound the chance, right? So let us apply the confidence inequality, right? So here, the true mean is replaced by the true error, right? And the empirical mean is replaced by the training error. It's just a direct, outright application of the half density inequality. Okay. And then we get this bound will be less than or equal to e to the power of minus 2m. M is the number of training examples, and epsilon squared. Epsilon is the some epsilon you're given. So now we'll get our result, right? The probability that a single hypothesis H has a true error that is more than epsilon away from the training error is bounded by this guy. This is a direct application of the agnostic learning. So far, any question regarding this result? Is everyone comfortable? Okay, if you still feel a little bit uncomfortable or even a little bit unclear, don't worry. Just look at the slides again, and just follow. We have discussed. You'll get it. So it's not hard. Okay, but this is just the very first step, right? Because this result, I mean, direct application of the Hopkins equality just tells you, okay, given some particular hypothesis, what is the chance that its true error of this hypothesis epsilon away from the training error made by this hypothesis? What is the law? What is the upper bound, right? But when we do the machine learning, right, learning algorithm looks for the best one in the hypothesis space. Actually, you don't know which particular hypothesis will be picked up or chosen by a learning algorithm. So to get a more robust and more comprehensive result, right, we actually want to know the probability there exists a hypothesis in the hypothesis space whose true error is epsilon away from the training error. What's that bound? And this bound is pretty easy to obtain. You just multiply the previous bound by the size of hypothesis space. How can we get this? We'll apply the same trick we used before. Right? So this is kind of existent statement, right? So basically it says, okay, there exists some hypothesis whose true error is epsilon away from the training error. This event can be decomposed as a union of set events. Right? It's like, okay, the first hypothesis whose true error is more than epsilon away from the training error, or the second hypothesis whose true error is more than epsilon away from the training error, blah, 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 until the last hypothesis in hypothesis space whose true error is epsilon away from the training error, right? So this event is actually the union of all these events, right? And according to the union bound we have used before, we know the probability of a union of events is upper bounded by the summation of the probability of each individual event, right? And the probability of each individual event is upper bounded by this guy, the same bound, right? You just essentially just add the same bound again, right? So finally, it gives you just multiply this bound by the total number of hypotheses in hypothesis space. Right? Does it make sense? Right? It's just the same trick as we used for the consistent learner. If you forgot when we use that or how we use that, please look back at the previous slides about the consistent learning. Okay. So now we have arrived at the our result that in the agnostic learning setting, the probability that there exists some hypothesis in the hypothesis space whose true error is epsilon away from the training error is bounded above by the hypothesis space size times e to the power of -2 m epsilon squared. Again, m is a number of training examples, okay? And epsilon is some level you want to probe, right? You want to know, okay, what is epsilon is 0.01, what is chance? What if epsilon is 0.1? What is that chance, right? But of course, when we have this bound, right, we actually want this bound to be as small as possible, meaning that we want our true error to be close to the training error as much as possible, so that, okay, once I get the training error, this is always easy to get, right? I can use that to safely to estimate the true error or the generalization error, right? So I want to designate a level of delta such that this event to happen will be less than or equal to delta. Like, I don't want the chance that my learned hypothesis whose true error is epsilon away from the training error. I don't want that chance to be bigger than epsilon, to be bigger than delta. Right? Then how can we make that? Right? How can we manage to get that? We're gonna play the same game before. Right? If we want our learned hypothesis, right, whose true error is epsilon away from the training error, this chance no more than delta, right? We can just solve the inequality that this upper bound is no more than delta, right? Namely here, right? And of course, we want to solve this inequality in terms of number of training examples. That's the only way we can reduce such a chance. I can imagine like the more training examples I have, right, the more possible the training data cover the whole instance space and reflect data distribution, and then the more likely the training error can reflect the true generalization error. So to quantify such a low bound, to the number of the training examples, right? So we can solve this inequality, and it is pretty easy to obtain that when m, the number of training examples, is bigger than this guy, then the chance that you can find out some hypothesis whose true error epsilon away from the training error will be less than or equal to delta, right? The given the designated level. Right? So now we get our sample complexity bound for the agnostic learning. It guarantees that for any offset epsilon, right, and probability level delta, right, if the number of training examples m is bigger than this guy, we guarantee with probability at least 1 minus delta, right, with you can roughly will is with high probability, your true error will not off by more than epsilon from the training error. So actually, this sample complexity bound just gives you at least how many training examples you need to train your model to ensure that, okay, the difference between the generalization error and your training error will be less than epsilon. It's not exact or absolute level of the generalization error. It's just relative difference between the true error and the training error. We'll get to that point later when we contrast the two consistent learning, right? So look at this low bound, right? So epsilon indicates the difference between the generalization error and the training error. Remember, epsilon now here is not absolute generalization error. It's just difference between the generalization and the training error. Right? How much worse? It indicates how much worse will the classifier be in the future than it is at the training time. And here, log size of hypothesis space H still indicates the complexity of the learning model. Right? So from that, we can still see the justification of Occam's razor's principle. So you can imagine given the same epsilon and delta, right? Meaning that you want to maintain the same high probability, maintain the same difference between the true and generalization error. The more complex machine learning model you choose, the more training examples you will need, right, to achieve epsilon, same epsilon and delta. So you can see it still prefers a smaller set of functions or smaller set of hypotheses. Right? In other words, if your H is small enough, then the number of training examples you need will be smaller. And this guy is obviously reasonable. Like the more confidence you want, like, that means the smaller delta is, then the more training examples you will need as well. So any questions so far? Yeah, that's a very good point. Here we're still assuming that your H is finite. So meaning that as long as your H is finite, we can we know that the size of H, right? But later we'll talk about what if H is infinite. If H is infinite, then this lower bound is not meaningful at all, right? Yeah, like even for linear classifiers, you know the weights are continuous, right? That means your hypothesis space is infinite. You have infinite choices of weights. Other questions? Okay, so in addition to the sample complexity, if we switch epsilon m, right, we actually can get a generalization error bound. So it's just to tell, okay, for any choice of training examples, right, we can guarantee that with high probability, which is at least 1 minus delta. So remember here is essentially epsilon. The difference between the generalization error and the training error will be upper bounded by this guy. Right? This is just if you switch m epsilon and then take a square root, right, to get epsilon here, right, it will be upper bounded by square root of this logarithm of size hypothesis space plus logarithm 1 over delta over 2 m. M is number of training examples. So this actually give us a feasible or very practical way to estimate the generalization error. Although we cannot give, okay, what is the exact generalization error, but we can give some bound, right? And the bound of the generalization error is that, okay, your training error plus something, right? And the additional term plus the training error, which is added to training error, is determined by the model complexity, right? And also determined by the number of training examples, and determined by the confidence level you want, right? And this is reasonable because the more training examples you have, you can see that this addition term is smaller, right? That means the closer your generalization error to the training error, right? And of course, it still favors smaller hypothesis space, right? Because the smaller or the simpler the model you have, the smaller the log size hypothesis space. That means the difference between the generalization error and the training error is small. We're going to reach to this generalization error bound later, right? And it actually, you see that the generalization error bound motivates the development of the support vector machines. Okay, so far we have seen two learning cases. One is consistent learner, right? The other is called agnostic learning, right? So consistent learning assumes that, okay, in whatever training data set, you always can find a hypothesis which gives zero training error. Right? In that case, we derive a sample complexity bound that with high probability, as long as your m, the number of training examples, bigger than this, then with high probability, your learned hypothesis, its true error will be less than or equal to epsilon. So here we're talking about the true error. Right? However, in the agnostic learning setting, this sample complexity bound tells you that when you satisfy this bound, right, the difference between the true error and training error will be less than or equal to epsilon. So just be careful the difference of the two settings, right? The results. So the second one, it just tell you, okay, your true error is no more epsilon away from the training error. Right? You need to account for the training error because the training error is not guaranteed to be zero. Right? So in other words, you can view, okay, it just tells you, okay, if you have so many training examples at least, and then your true error will be no bigger than epsilon plus your training error. Right? As to how much training error you get, it really depends on your algorithm, the learning algorithm. Right. So from both sample complexity bounds, we can see that it depends on the log size hypothesis space, as we just mentioned. Right? This actually implies your hypothesis space is finite. But what if your hypothesis space is infinite? And it's not unreasonable to assume an infinite hypothesis space. Right? Even for linear classifiers, we know that linear classifiers determined by the weight parameter and bias parameter, right? those weights and bars are all continuous variables. Okay? So that means you have infinite choice of W and B, and gives you an infinite hypothesis space. Right? We can see that even for relatively simple classifier like linear classifier, the hypothesis space can be infinite, and that means you cannot use these two results to analyze the sample complexity bound or generalization error bound, even for linear classifiers. Right? That's really, really restricted. So some previous analysis we have done so far was restricted to finite hypothesis space. Right? But someone may ask, okay, suppose we got infinite hypothesis space, because they're both infinite, right? Like you have two hypothesis spaces, right? Both are infinite, right? Shouldn't they be equally expressive? The answer is no. Right? So here we just give some example, right? For example, you got three hypothesis spaces. The first one are rectangles. The second one are 17 size convex polygons. And the third one is just general convex polygons. And of course, all of those three hypothesis spaces are infinite, right? So now I'll ask, which one do you think is more expressive? Yes, exactly, right? Why? Because rectangles can be viewed as a convex polygon. 17 size convex polygon, of course, is a convex polygon, right? So every element in these two hypothesis spaces also belong to the general convex polygon polygon space, right? So actually, the rectangles and 17 size, they're just subsets of the general convex polygons. Of course, this guy is more expressive than the remaining two. Right? If you look at a linear threshold function, which is just linear classifier, right? There are obviously infinite hypothesis space. But if we do a linear combination of these linear threshold functions, which one is more expressive? The second one, right? Why? Because one single linear threshold function is just one instance of the combination of linear threshold function, right? You have many other choices. So you can see that, okay, although the hypothesis spaces can be infinite, right? We can still compare their expressivity. Then the problem is that how do we compare them? First, we need a measure of the expressivity of an infinite hypothesis space other than its size. Right? If we just use their size, okay, as long as infinite, size is infinite, right? You cannot, it's not comparable. You cannot compare infinity with another infinity. So we need to define another finite measurement over infinite hypothesis space. Right? So there can be different measurements, right? Here we're going to discuss, the famous VC dimension. The full name is Vapnik-Chovanecky's dimension. Right? So VC dimension gives such a measure over arbitrary hypothesis space. This space can be finite, can be infinite. So you can view it as a counterpart to the size of hypothesis space. However, it is more broadly useful because for most infinite hypothesis space, the VC dimension can still give you a finite number so that you can directly compare for the comparison. So we're going to use a concrete example to showcase of this motivation. Okay? So suppose we want to learn a rectangle, right? So this is a rectangle classifier because the rectangle is determined by the points on the current corner. So you can, those points are continuous. That means the hypothesis space is infinite. Right? So suppose this is your target function, right? The target concept. Right? And our classifier will classify all the points inside as positive. Right? Inside as positive, and the points outside as negative. Okay? So at the beginning, you can imagine, okay, if I only give 4 examples, 3 examples, 2 positive and 1 negative, right? You run your learning algorithm, you might just end up with this guy. Okay? and it says 0 training error. But of course, the learned rectangle classifier is far away from the ground truth. So now, if you increase the training data size, right, you add more training examples, well, the learned rectangle will get closer to the target rectangle, right? You just keep doing that, from the trend, we see that, okay, with more and more training examples added, we'll eventually learn a rectangle very close or arbitrarily close to the target function, the target rectangle. So that means, okay, even for the infinite hypothesis space, even you have like numerous possible choices of rectangles, as long as you keep adding training data with sufficient data, you're gonna still find hypothesis closer and closer to the target function. Right? But of course, the first to answer this question, like the learnability of this target function, we need to know, okay, how expressive, what is capacity of this rectangle hypothesis space. That's where that's how this VC dimension is motivated and is invented. Right? So before we consider the expressivity or capacity of rectangles, right? Let us first reduce the hardness. We just look at the lines. We just look at lines. What about the expressivity of lines? Right? Suppose we're given 2 points, arbitrary 2 points. And again, we will consider binary classification problem. And if we allow to arbitrarily label these 2 points, we got 4 possible labeling schemes, right? Positive, negative, 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 positive, and positive, positive. Right? So we can examine that under arbitrary labeling scheme, if we can find out a line which can perfectly classify the 2 points. Right? In other words, if we can perfectly label, predict the labels of the points. For the 2-point setting, it's easy. Right? For any labeling scheme, like you can see there are 4 labeling schemes. For any labeling scheme, we can always find a line in our hypothesis space which can perfectly separate out the positive examples and negative examples. So we call linear functions or linear function hypothesis space are expressive enough to shatter 2 points. This is the idea of the shatter. So now let us move to a more difficult example. So what if I got 14 points? So this is where these 14 points locate. So I want to ask, with this set of 14 points, are they still be able, is our linear function hypothesis space still able to shatter these 14 points? Yes? Why do you think it's yes? Yeah. But here I want to emphasize again, like if we see shattering, means that for any labeling scheme, you can well separate the positive and negative examples. Yeah. In fact, this is very hard and infeasible for these 14 points. Why? Maybe for one particular labeling scheme, well, like this and this, okay, I can find a line which will separate positive and negative examples. Right? However, if I switch to another labeling, right, like this very mixed labeling, right, you won't be able to find any line to separate out positive and negative examples. Right? You can try that. You can try them horizontally. Right? You can try a lot, right? So actually, you won't be able to find a line which can separate all the positive examples from negative examples. In fact, if you want to do that, you have to use some like curve. In other words, we arrive at a conclusion that linear functions are not expressive enough to shatter 14 points given here. They're expressive enough to shatter only 2 points. And later we'll see they are able to shatter 3 points. But for 4 points, they cannot shatter n. Okay, let's stop here today. And next class, we're gonna give a formal definition of shattering. And based on shattering, we'll give the definition of VC dimension. And we'll introduce the VC dimension for several commonly used hypothesis spaces. Okay.